Welcome back. So today in our second lecture, we are going to discuss functions. A nice way to conceptualize functions is by drawing a box and saying that what a function does is it accepts things called inputs and it produces things called outputs. And the output is not allowed to be ambiguous. That's part of the definition of a function. So let's imagine this is a function here that accepts numerical values as inputs. So let's imagine that the number 1 is an allowed input. Well, I don't know how, but let's just say this function is going to use the input of 1 and produce a corresponding output of 5. And this value is not ambiguous. There's a definitive value for the output. Okay. Now let's imagine there are also other possible inputs here, that f can accept an input of 3 or f can accept an input of 7. And f, through mechanisms that I don't really know yet, is going to take the input of 3 and produce an output of -2. F is going to take the input of 7 and produce an output 1/4. Now I've left the inside of this blank because I'm trying to communicate that I don't understand how the function did this, but I need to be clear that the input of 1 is not going to give me this, or that, because that would be ambiguous. The input of 1 is going to, by some interesting mechanism, produce a definitive output of 5. Same thing with the 3. The 3 is going to produce a definitive output of -2, and then the 7 is also going to produce a definitive output. Okay. Now, the values over here, let's imagine these are the only values that the function can accept as inputs at this stage. We call that the domain of the function. The domain is the set of all values that can be accepted as inputs. And over here, we have the range, which is the set of all of the values that can be produced as outputs. Then perhaps it suits us to give this function a name. Let's go ahead and call this function f. And we can use the following notation to represent the information in the picture above. So the pattern here is the number inside the parentheses is the input. And then this f right here represents the name of the function, and then the number over here represents the output. So the way we read this is we say f of 1 equals 5. Means if you take the input of 1, the function f will produce the output of 5. And we say f of 3 equals -2, f of 7 equals 1/4. Okay. What if I ask the question, what is f of 2? So that would be saying, if the input is 2, what does the function f produce as output? But if I look at the domain, the number 2 is not in the domain, which means the number 2 is not a valid input for the function f. So I cannot get a valid output. This is undefined. Hence, the idea of a domain becomes incredibly important. Okay. And of course, in this context, I can ask the reverse question, what is the value of x such that f of x equals -2? And this is effectively an equation that wants me to find a value for x. This is kind of like saying solve. Okay. Well, I know the output is -2. So if I look at my function, there's only a single input that leads to this output. And I can say, the only input there would be 3. So I would say x equals 3 is the answer to this question. Let's open up a new discussion. Let's consider g of x equals 3x minus 1. Okay, so what this says, this thing in the parentheses is the input, and I'm letting that be a variable this time. And the thing over here on the right, this is supposed to be the output. This is an expression this time. So what I'm communicating is, if I pick a value for the input, then I can evaluate the output according to this expression. And this information put together, we call a function rule. Okay. So let's imagine I want to find what g of 0 is. That would mean use 0 as the input and then tell me the output. But remember from the previous discussion, we need to decide if the value 0 is part of the domain, meaning can we use 0 as an input? And usually when we define the function, we are going to specify the domain as well. So in this case, let's just say x is allowed to be any real number. So we can write that x is an element of the set of real numbers, and this is going to be the domain. And oftentimes, if you don't specify anything, then it's assumed that x can be any value that you could evaluate this expression for in a legitimate way. Okay? So if I do g of 0, that means I will use 0 for the value of x, which means I have to use 0 for every value of x that appears. So that'd be 3 times 0 minus 1. I could do something similar and say, what is g of 5? So that means 5 is being used for the value of x. 5 has to be used for the value of all the x's. So that'd be 3 times 5 minus 1 is 14. And we can do this in the calculator by the following. I can write g of x, and I'm going to use the colon equals. That's going to be control and then the button next to the library catalog. And I'm going to say 3x minus 1. When I hit enter, it says done. And the calculator is going to assume that the domain is anything that it can use to evaluate this function. So if I type g of 0, it gives me an output of negative 1. If I say g of 5, it gives me an output of 14. So far, everything is the way we predicted. Then we can take this information and say, well, maybe a table is a suitable way to represent things about g. So I can make a table like this. And over here, I'm saying these are going to be the values that I use for x. So maybe I will use negative 1, 0, 1, 2, and 3. And then over here, I'm going to say this is going to be whatever happens when I use negative 1 for the x. So effectively, this is saying, tell me what g of negative 1 is. This is saying, tell me what g of 0 is. So if I were to do that, then I would say this is negative 3 minus 1. I'm going to go ahead and put this in red, negative 4. I will write the rest of these and then fill it all out in red. So g of 0 would be 0 minus 1. G of 1 would be 3 minus 1. G of 2 would be 6 minus 1. And G of 3 would be 9 minus 1. Okay, so far so good. But whenever we have information that we can catalog, we often start to think, is there a way we can represent this using a graph? Because a graph is very visually nice. So in life so far, we have represented many things on a graph in the xy plane. And what that means is we want to come up with ordered pairs, so combinations of values of x and y that satisfy some kind of relationship. So it might make a lot of sense to say, well, we have a table, we have an x in the function rule, the x coordinate of whatever we place on this graph might take on the value of x. But then what should we use for the y? Because I don't see a y anywhere above this on the paper. So we say, why don't we take the output, g of x, and use that number for the y? So you'll often see a graph that says y equals g of x. And that's exactly what that means. It says you take the x value, get the output, whatever the output is, you're going to make that the y variable. So if I were to go up here and say, okay, let's make an ordered pair for each of these rows. So when x is negative 1, the output is negative 4, and that's going to become the y value. So I can say this is negative 1 comma negative 4. And then I can do the same exercise. When x is 0, the function output is negative 1. That's going to become the y value. So this would be 0 comma negative 1. Then here, when x is 1, g of x is 2. When x is 2, g of x is 5. When x is 3, g of x is 8. And this is why when we teach functions, we often say that writing g of x is sort of synonymous with just saying y. Y equals 3x minus 1. Okay, now look, this looks very familiar to us. This is the equation of a linear relationship, which means if we graph it, we're going to get a line. And in fact, we can go to the calculator and say, let's make a new page. We will call this a graph page. And last time, I changed the input mode to relation. And this time, I'm going to leave it as a function. And by default, the first thing that shows up, we call this f1 of x. So perhaps we could just say, okay, whatever the first thing is, I'm going to set that as g of x. So what this is telling the calculator is, for the graph I want, I'm going to use g of x as the function that I want you to graph. And specifically, I'm telling the calculator, I want you to produce a graph where y equals g of x. And if I hit enter, that's the graph of a line. Because remember, of course, this number here, this is the slope, and this number here is the y-intercept. So we look at that and say, oh, that's going to be a y-intercept 0, negative 1, and the slope is going to be 3, so that's up 3 over 1, and we have this nice graph that we can see on the screen. Okay, so now we have a way to discuss how to represent functions in graphs. And do keep in mind that the way I describe this calculator thing might be a little bit strange or technically confusing. Don't let that bother you. If you just think to yourself, oh, g of x or f of x, that's just the same thing as y, you're going to be fine. Let's continue the discussion with a brand new function h of x with a specified domain. So the input value x can be any one of those. And we have a table that illustrates the behavior of h. We can use some commands like the following. You can say find h of negative 1. So that means if the input is negative 1, go and find the output according to the function h. Well, in the table, x is the input. So if the input is negative 1, the output is evidently 7. So we can happily conclude h of negative 1 equals 7. Life's good. And what if the command is find h of negative 3? Well, we know the domain does not include the value negative 3, which means negative 3 is not a valid input for this function h, so we cannot get an output. We would say, oh, h of negative 3 is undefined. Okay, so far everything is consistent. Now, what if I then ask the question, find the value of x such that h of x equals 0. So what this is saying, like we did before, 0 is the output according to some input x, and we need to go find the input that gets us an output of 0. So if I look on the output side, I detect the number 0 right here. And I ask myself, what was the input for that? Oh, the input must have been 1. So my conclusion will be that x equals 1. Now, this action that we performed of using the output to go back and find the input that would produce that output, we're working backwards. And this is what we call an inverse operation. Okay. So the way I'm going to end up writing this, okay, is I'm going to say h of 1 is equal to 0. Okay. And then I'm going to write something very interesting. I'm going to say h inverse. And in the parentheses here, I'm going to put the 0. Okay. Now, what this means to us is it says, I'm going to do the inverse version of h. So I'm going to work backwards. And I'm going to use 0 as the input for working backwards. Wait, what does that mean? Okay, so if I'm working backwards, then I'm going to start with whatever the output value of h was. So this is normally the output of h. But since I'm working backwards, that's what I'm going to start with. Okay? If I'm working backwards, I want to ask myself, what could I use as the input in order to get an output of 0? Well, it turns out the answer is 1. So this is the value of h inverse of 0. Okay, let's do another example really quickly. If I say h of 2 equals negative 1, then that means when I use an input of 2 with h, then my output is going to be negative 1. So if I work backwards, I would say h inverse. Working backwards means I'm going to start with the output value of h, and if I start with that working backwards, I will get the input value 2. So now, I want you to be very careful about this. This negative 1 is not a power in the sense that I'm not dividing something by h. This is not 1 over h. This notation means I'm doing the reverse version of h. I'm doing the inverse of h. And so really what that means is I'm going to start with what is normally the output, and I'm going to produce what is normally the input. We can think of this as switching the output and input. Or in the world of a graph, we might think of it as switching the x and the y. So this is really what the word inverse is going to mean for us in the context of functions. Let's keep the discussion going with a brand new function. So here I have a function rule. So the input is going to be a variable x, and once I know the value of x, I can evaluate this expression to get the output. Then I'm saying the domain is the set of all real numbers. So for example, I could ask you to find j of -2. And you would use -2 as the input, so that would become the value of x. So I'd put -2 in for all of the x's. I would happily conclude that j of -2 is 5 times -2, which is -10, plus 2 is -8. Okay. Now, what if I asked you the question, or I gave you the command, find j inverse of -8? Okay, so that means work backwards. So start with what's normally the output of -8 and go back and find me the associated input. Well, I already know the answer because I found that if the output is -8, I can trace it back to an input of -2. So I can immediately conclude that j inverse of -8 is -2. But this raises the question, what if I never did that? How could I have known that j inverse of -8 would become -2? Because what if I then asked you, find j inverse of 7, for example? Well, that means work backwards. I'm going to start with an output value of 7 for the function j of x. Wait, that just means I need to make sure that this expression is going to evaluate to 7. Wait, doesn't that mean I can just say 5x plus 2 is equal to 7? That's exactly what it is, right? So we can think of this as, since this is supposed to be the output, we can take the function j of x and set it equal to 7. So this is reading j of x equals 7, find x. I'm trying to solve this. And now we have a linear equation. We can just subtract 2, say 5x equals 5, and then x equals 1. Which means we can conclude that j inverse of 7 is 1. Okay? Let's do another one, just for good measure. What if I want find j inverse of, let's go with -4/3. We can be even more obnoxious with this. So that means I need to work backwards. So starting with the output of j. So the expression j of x, this needs to evaluate to -4/3, which means I can set this equal to -4/3 and solve for x. All right? 5x plus 2 equals -4/3. Well, it's a linear equation. I'm going to subtract 2, also known as 6/3. So if I subtract 6/3, I get -10/3. And then if I divide by 5, then I would end up with -2/3. Oh, so I can happily conclude that j inverse, working backwards from -4/3, will get me -2/3. So now we can ask a really cool question. Can we generalize the idea of using the inverse of a function and then writing a function rule for the inverse of a function? So the command that would show up, perhaps in a lesson, would be find j inverse of x. Okay, so let's lead up to this in several steps. So if I have that j of x is equal to 5x plus 2, and let's just call this a y value for now. Okay, right? When we graph things, we would just take the output and assign it to y. Now, we could conclude that working backwards, if I did j inverse of y, so whatever the output of j is, I would start with that using the inverse, and that would give me back what I used as the input, right? And hopefully this makes sense based on what we did in the previous discussion. Okay. So what if I then take this and say, okay, if I write 5x plus 2 equals y, then can I isolate for x and figure out what that is in this context? Well, that would be the same thing as solve for x Well, we can do that. So we can move the 2 to the other side. That becomes y minus 2, and divide by 5. So I would say x is equal to 1/5, parentheses, y minus 2. So then if I say x, which is over here, is represented by the expression 1/5 times y minus 2, couldn't I write J inverse of y equals 1/5 times y minus 2? It's a rhetorical question. The answer is yes. I have been consistent in all of this. Assuming, of course, that it's even possible to discuss what J inverse is, which in the next lecture we'll talk about those subtleties. So in this case, I have a statement. This is a function rule. But in the original command, it didn't say find J inverse of y. It specified that I need to use the letter x to represent the input. So in order to properly answer the question, I would have to say, oh, well, I mean, y is just a letter. It could be any other letter to represent a variable. So I could swap out all the y's for x's or z's or w's or whatever letter you want, right? And this is the exact same information. The only sort of annoying part to the student, perhaps, is that we already used the variable x up here to indicate the input of j. But when we talk about the inverse and we put the x in here, certainly, the inverse, as long as it's a function, can take an input with a variable x. But that x, when we're working backwards, is whatever the output was when I used the original function. So the x in this line is not going to be the same as the x in this line because they represent different ideas. Over here, the x is the input of j, and 5x plus 2 is the output of j. Over here, the letter x is the output of j, because we're working backwards. And then this expression is going to be the associated input of j. Okay, so if we put all that together, hopefully we can understand the following sentence. Okay. If you take a function with an input and output, then the inverse function switches those. So the output of the function becomes the input of the inverse, and the input of the function becomes the output of the inverse. We are switching the x and the y. Now, let's go back and think about a function we defined earlier with a domain that was all real numbers. So you can see that on my calculator screen. We defined g of x earlier. Now, what we want to do this time is find a function rule for g inverse of x. Okay. Let's understand what that means. So here, in the original function, x is the input, and this expression is the output. So perhaps we could write a relationship that says y equals 3x minus 1. Right? So I'm taking the output and I'm replacing it with the letter y. Now, in order to find the inverse, we're supposed to work backwards. Staying with the rhetoric of switching the input and the output, this is what I'm going to do. I'm going to take the x and the y and switch them. Okay. So I'm going to cross this out and write x equals 3y minus 1. So in this context, what I want to understand is, in the original, this x was the input of g, okay, and the y was the output of g, so the original function. But now down here, this letter y, because I usually think of y as output and x as input, right? This is how we write functions. So this is going to be the output of what, though? It's the output of g inverse of x. Okay. And this x right here is the input of g inverse of x. Okay, so we switched the letters, but we actually haven't changed the way we understand math. Okay? Because the input of the original function, when you work backwards, is going to be the output of the inverse, right? Because you're switching the input and output. Input of the original is the same thing as output of the inverse. Similarly, the output of the original is the same thing as the input of the inverse, because you're switching the input and output. And this is why we say switch the x and y. And then since our goal is to find g inverse of x, that's the output of g inverse of x, we're trying to isolate for y. So if I add 1 to the other side, I get x plus 1 equals 3y. And then I'm going to divide by 3, so that's 1/3 x plus 1 equals y. And my conclusion then is g inverse of x is 1/3 x plus 1. Okay, so the procedure, once again, we teach it as write down a relationship for the original function, then switch the x and y. Once you have switched to the x and y, you isolate and solve for y, and that result is going to give you the inverse. Let's confirm one more thing, and then we'll be done for today. So here was a function we defined, and we then derived this as the rule for the inverse function. So if the command is find g of 4, then that means use 4 for the input of g. So x is 4, that means this x is 4. So we could say g of 4 is equal 3 times 4 minus 1, so that's 12 minus 1 is 11. Okay. Then if we want to find g inverse of 11, we understand that we're switching the input and output when we go to the inverse. So here the input for the inverse function should be the output of the original function. And then the answer to this, the output of the inverse function, should match the input of the original function, switching the input and output. So the answer here should be 4. Now let's check that using the function rule. G inverse of 11 means take 11, use it as the input here. That means x is 11. That means this x is 11. 1/3, 11 plus 1. That means 1/3 of 12, which is 4, and that is the answer we expected. So things are consistent. And you can check this for other values if you so desire. So that's the end of today's lecture. Thanks for tuning in. And next time we'll talk about the subtleties on when can you even find an inverse function? Because you can't always. And then we'll talk about what happens to the domain and the range, and then we'll talk about what happens to the graph. Take care. I'll see you next time.